Good evening to all, and welcome to the another session of the NPTEL course Heat Transfer. So this is our seventh section, or we can say the seventh week session. So today we will be discussing about the contents that were discussed in the week seven of this NPTEL course, which covers the internal flow heat transfer, or we can say the flow through an internal pipe or a duct. So today we will be discussing some of the practice questions related to this topic. So let's have a brief recap of what are the uh, connects that are discussed in their flow. So in the previous week, what we discussed is the flow, external flows, where the flow through a flat plate. But in this week, or the week seven, where the main topic was the internal flow, or the flow through a confined boundary. Okay, it will generally say the flow through a pipe. So in that case, we have studied, we have looked at aspects like constant flux boundary condition, constant temperature boundary conditions, and the relationship or the energy balance, etc., were derived with respect to these kind of conditions, and what is a fully developed flow, and what is a thermally developed flow, and also the Nusselt number of constant heat flux condition, constant temperature condition. These kind of uh, topics were discussed, and also the correlations for different types of situations were also discussed. So today we will start with the first question. So we have a system for heating water from a inlet temperature of 20 degrees Celsius to an outer temperature of 60 degrees Celsius, involving passing the water through a thick walled tube having inner and outer diameters of 20 and 40 mm respectively. The outer surface of the tube is well insulated, and electrical heating within the wall provides a uniform heat generation rate of 10 raised to 6 watt per meter cube. And we have the mass flow rate of water is also given. And the question is, how long must the tube be to achieve the desired outlet temperature? So you can start doing it. After that, we will discuss. I hope the question is clear. So we have a pipe. So we have some set predefined inlet and outlet temperature, and the heat generation is happening inside the tube. So our question is to find out how long the tube must be to achieve this desired outlet temperature under these conditions, like the specified mass flow rate as 0.1 kilogram per second, and the specified uniform heat generation rate of 10 raised to 6 watt per meter. You can start solving. After that, I will solve it for you. Did you got the answer?
No, sir.
Okay. Uh, so what we have is a tubular pipe, sorry, annular pipe. So the water is entering the pipe at 20 degrees Celsius, and the water should exit the pipe at 60 degrees Celsius. And the length of the pipe, we don't know, we have to find out. Mass flow rate is given, that is zero point 0.1 kilogram per second. And it is said that the outer surface of the tube is insulated. So what it means? And it
It,
has
it means that whatever heat is generated, that
yeah,
heat is being absorbed by the water.
by the water. Okay, yeah. So that is a energy balance. That is whatever heat is generated, there is no loss to the ambient. It is it is coming to the water. Okay. So and its inner diameter is given. But how much? Inner
20 mm.
diameter is given as 20 mm, and the outer diameter is given as 40 mm. So let it be di and do. Okay. So what is the volume of this pipe?
Sir, it should be pi by that pi by 4 do minus di square into length.
Do square minus di square into length. Okay. So it is given the volumetric heat generation rate. So what is the total heat generation or the net heat generation in watts? How we calculate? Q dot into V, right?
Yes,
So
sir.
so this is the total heat generation in the pipe, and this heat should be taken away by the water. Am I right?
Yes, sir.
So this should be equated to mcp dt, tmo minus tmi. Am I right?
Yes, sir.
Yeah. So this much only. Just you need to substitute, that is q dot we know. Then pi by 4 do square minus di square into L is equal to mcp tmo minus tmi. So only unknown is L, which we need to find out. And the CP you can take it as
4
forward
point
uh,
4.182.
uh, 10 raised to or kilojoules per kilograms Kelvin. So can you please calculate and say what is L? Because everything we know, Q dot DO DI. Now just calculation, that is M dot CP TMO minus TMI by Q dot into pi by 4 DO square minus DI square. This is equal to M dot is 0.1 4127 60 minus 20 10 raised to 6 pi by 4 DI is DO is 40, so 0.04 square minus 0.02 square. So what is L?
1.1 meter.
1.1 meter. So can you please cross check? It should be close to some 17.
Now it is coming out to be 55.
55.
Yeah, I think it is. In calculation mistakes.
I think some calculation mistake is there. So it should be around 17 meters. It is what I am getting. Okay, otherwise I will also calculate once.
So it's coming out to be 55.
55.
Yes.
Let me check. Okay, you will go to the next question, and by the time you solve, I will recalculate it. Okay. So I hope the concept is clear. So
Yes, sir.
I will just recalculate it and say.
Okay, sir.
So we'll go to the next question. So we have the water which flows through a 2.5 centimeter internal diameter in copper tube of of a heat exchanger at 50 degrees Celsius and at a rate of 0.3 kilogram per second, and is heated by a steam condensing outside at 120 degrees Celsius. Okay. If the average heat transfer coefficient is given some 800 watt per meter square Kelvin, what is the length of the tube required in order to heat the water to 115 degrees Celsius? So here the question is, we have a thin wall copper tube, and water is entering, its diameter is given. Water is entering at 15 degrees Celsius at 0.3 kilogram per second mass flow rate. And on the outside surface of the tube, steam is condensing at 120 degrees Celsius. And we have to heat the water from 15 to 115 degrees Celsius. And our heat transfer coefficient is also given. So we have to determine the length of the tube in order to heat the water. I will. So you may please try. So by, uh, by the time I will just recalculate the previous one. So the previous question I recalculated it, so I'm getting some 17.7. So you please check your calculation.
Okay, sir. I will check.
Okay. Are you able to solve this?
Sir, I am just trying.
Okay. Can you please say what is the boundary condition? Means we have studied two types of boundary conditions. It's constant heat flux and constant temperature. So which one comes first?
It
Oh,
is constant surface heat flux
how? Can you please explain? Why you
because
why why you think like that?
because the heated by steam condensing outside at 120 degrees Celsius. So the
Okay.
temperature on the tube is maintained at 120 degrees Celsius.
Yeah. So it's a constant temperature, surface temperature.
Yeah,
It's not
constant
constant.
surface. Oh,
It's not
sorry, it is
constant.
constant surface temperature. Yes, sir. Constant
Yeah.
surface temperature. Yeah,
Yeah. It's a constant surface temperature condition.
yeah,
It's not constant heat flux.
yeah. Constant surface temperature. Sorry.
Yeah. So I think now then you can solve very easily.
But sir, question is, will we be introducing here the concept of LMTD?
Yeah. You should introduce. So I'm giving some 2 more minutes. I hope you will be able to solve it. Or should I start?
Sir, you start.
Okay. So in this question we have a tube of so we have a thin walled copper tube. So its diameter is given as 2.5 centimeter, and water is entering at zero point 0.3 kilogram per second, and the temperature TMI is 15 degrees Celsius, and it should be heated to a exit temperature of 150 degrees Celsius, and the steam is condensing. Steam condensing at 120 degrees Celsius. So we are asked to find out what is the length of the pipe required to heat the water to 150 degrees Celsius. So what is the Q? It is H, A surface area, and LMTD, right? So how we will find the LMTD?
So delta
Delta
T2
T
minus.
minus delta Ti divided by ln delta Te by delta Ti.
Yes,
So
sir.
what is delta Te? Tmo minus Ts, right?
Yes,
Or
sir.
Tmi is equal to Tmi minus Ts. So or we can take the reverse also, but it will Anyway, it will be same because here the TS is greater. So what it is not going to affect the final LMTD. So this is some 5 minus 10. How much? 105 divided by ln 5 by 105. So what is LMTD? Can you please calculate? Are you getting some 32.85 degrees Celsius?
32.85, sir.
Yeah. So now we got what is Q is equal to H is already given to you. So some 800, right? Yeah.
Yes, sir.
What is the surface area?
Pi dl.
Yeah. Pi into D is given. How much? 2.5 L. So that is what we need to find out. And LMTD is 32.85. So this should be equal to MCP dt, right?
Yes, sir.
So can you please calculate what is L? That is MCP dt divided by H by dl.
So, sir, value of CPA should be 4127
Value of CP you can take it as 4187
units.
joule per kilogram.
Okay.
Sorry. So M is given us so what is L? Can you please calculate and see?
So it's around 60.9 meter.
How much?
60.9.
Yeah, almost close to 60.9. Okay. Then let's move on to the next question. So we have the water, which is to be heated from 15 to 65 as it flows through a 3 centimeter internal diameter, 5-meter long tube. The tube is equipped with an electric heater that provides uniform heating throughout the surface of the tube. The outer surface is well insulated so that the heat, steady state, all the heat generated is in the heater is transferred to the water. If the system is to provide hot water at a rate of 10 liter per minute, determine the power rating of the heater. So this is just the like opposite of our first question. So I hope you will be able to solve it. So I will wait for 2 minutes. Please solve it. It's just a single line solution, so you can solve it very easily. Are you able to solve it?
Yes, sir.
Yeah,
34, 34.4 kilowatt.
yeah, very good. So what we have to do is, so first Q is equal to m dot Cp delta T. This is what we need to find out. What is the Q? Okay. So what is m dot? Which is rho times the volume flow rate. Okay. So this is rho is already given, that is 992.1. The volume flow rate is given in liters per minute, but we need in meter cube per second. So we have to do the appropriate conversions, like from, that is from liters to meter cube and from meter to second. So you'll get some 0.165 kilogram per second. Am I right?
Yes, sir.
Yeah. So now just direct substitution, that is Q is equal to 0.165 into Cp 4179 delta T is 65 minus 50, which is 34.476 watts or kilowatts. So what is the unit?
It should be kilowatt.
Yeah, kilowatts. So this was a simple question. So let's go to the well, next question, which is a continuation of the previous question. We have to estimate the inner surface temperature of the pipe at the exit. Okay. So please don't look at the options. So it's wrong. So we have to find out the inner surface temperature of the pipe at the exit, not the fluid temperature, the inner surface temperature of the pipe.
What should be the condition that it should be at a constant surface temperature?
No, no. It is equipped with the electric heater that provides uniform heating throughout the surface. So it's like
Okay,
a
okay.
pipe, okay, and we
Constant
are
surface
use
flux.
and we are wrapping a micro wire around this surface so that it will give heat. So if that condition is constant heat flux condition, so it's not a surface temperature. So we are so this so the condition here is the tube is having a constant heat flux. I hope you understood.
Yes, sir.
Okay. So this is a question. So what you have to find out is the inner surface temperature of the tube at the exit. Sorry. Okay, I will start solving this. So the heat flux is equal to H, the heat transfer coefficient, times TSO minus TMO. Okay, this is for exit. So we are asked to find out this TSO, which is equal to Tm at exit or outlet by Q dot S by H. So this TMO we are already known. That is how much? This is 65 degrees Celsius. Okay. So our main task is to find out Q dot S or the heat flux and H. Can you, how we can find out the heat flux?
That we have already calculated above.
Yeah, that is heat. That is the heat transfer rate. It's not heat flux.
Okay, that
Just
is the
divide
rate
by the
by the
surface
area.
area. Yeah.
Yeah, by dl.
So Q dot S is equal to Q divided by pi dl or the surface area.
Yes, sir.
That is 34.6 divided by pi into what is D? 3 centimeters and 5 meter long. So can you please find out what is this heat flux? I think it should be some 73.46 kilowatt per meter square.
Yes, sir.
So, so our first task is on, that is Q dot S we find out. Next is H we have to find out. So for H, for finding out H, we have to find out what is the Reynolds number of the flow. So for that, what is Reynolds number is rho Vt by mu or UM, that is mean velocity. So we have to find out the mean velocity first. It is UM. How we can find out? That is the volume flow rate divided by the cross-sectional area, because the volume flow rate is already given 10 liter per minute. Okay, so that is 10 raised to 10 into 10 raised to minus 3 divided by per second 60. Area of cross section is pi by 4 into 0.03 the whole square. Can you please find out what is the velocity, mean velocity of flow? I think it should be some 0.235 meter per second. Are you getting this?
0.236.
Oh, okay, fine. So can you please find out what is the Reynolds number? So rho is 992 mu. So this is kinematic viscosity. Okay. So we can write Vd by mu, which is equal to 0.236, 0.03 divided by kinematic viscosity 0.658 into 10 raised to minus 6. What is the Reynolds number?
10,760.
Yeah. So this is a turbulent flow, right?
Yes, sir.
Yeah. So for turbulent flow, we have the Ritter-Boiter equation for Russell number. This is discussed in the class, which is 0.023. Reynolds number raised to 0.8, Prandtl number raised to n, where n is 0.4 for
Heating.
heating and zero 0.3 for cooling.
Cooling. Yes.
So here it is heating, right? So the n should be 0.4. So What is the Russell number? Can you please find out? 0.023. Reynolds number is 107.8. Prandtl number is given as 4.34.
That's 69.5.
Yeah. Here we are making one assumption like the flow is fully developed. Okay. Then only we can use this Russell number correlation. It's please calculate this L by D. What is the length? 5 meter, right? Divided by 0.03. So if the L by D is greater than some 10, okay, we will assume that the flow is fully developed. So here our assumption is right because what is the L by D? Is anyway greater than 10. Am I right? Length is 5 centimeter, right? 5
Yes,
meter
sir.
and
Yes,
the
sir.
flow is okay. So our developed flow assumption is valid. So the Nusselt number, sorry, the H is equal to the heat transfer coefficient is K by D Nu. So K is how much? 0.631 into Nusselt number is 69.5 divided by 0.03. So what is the heat transfer coefficient?
Sir, 1462.
Yeah, 1462 watt per meter square Kelvin. So now you can now everything we find out. So can you please find out what is the surface temperature? This is 65 plus 7.3, 10 raised to 3.
Sir, it's 115.2.
Yeah, this is the surface temperature of the tube wall at the exit. Okay, so then we will move on to the next question. So we have a flow of a liquid metal through a circular tube. The velocity and temperature profile at a particular axial location may be approximated as this. U of r is C1 and T of r minus SDS is equal to C2 1 minus r by r0 the whole square. So what is the value of the Nusselt number at this location? I will give some 2-3 minutes for you to solve. Okay, I will start solving. So the velocity profiles is given as, just a bit. So the velocity profile is given at that location as C1, and the temperature profile is given as Ts plus C2 times 1 minus R by R0 the whole square. Okay. So for finding out Nusselt number, it is H, which is HD by K. Okay. So first we have to find out what is H. So H is the heat flux divided by surface temperature minus mean temperature at that location. I am saying about that location. Okay. So first we have to find out the mean temperature at that location. So what is Tm? That we already solved. That is 2 by um r0 square equals 0 to r0 t u t r dr. Okay. So so the u mean is the C1 itself, because why? There is no need of integration or something, because C1 is constant. Okay. So the mean temperature, the mean velocity will be C1 itself. There is no uh, variation along the radial direction. So if I substitute here, Tm is equal to 2 by um is C1 itself, R0 square, integral 0 to R naught, U is C1, T is Ts plus C2 1 minus R by R0 the whole square. Okay. R dr. So the C1 both cancels. So it's just integration. So 2 by R0 square. So if I integrate it, I will get Ts minus R square by 2. Sorry. Ts R square by 2 plus C2 R square by R square by 2 minus C2 R raised to 4 by 4 R square, because R square into R become R cube. So if you integrate R raised to 4, so this is the integration. So you have to put the limits. So after putting the limits, you will get Tm as Ts plus this R0. You can take common and cancel C2 by 2. Okay. You just substitute the limit and simplify it. So now what is Q dot S? That is heat flux is K dot T by dou R at R is equal to R0. That is the surface heat flux. Okay. So so if you differentiate this, that is which one? T of R, and put the limit R is equal to 0, you will get minus K C2 2 R by R0 square at R is equal to R0. So you will get minus 2 C2 K by R0 as the surface heat flux. So now it's just substitution, that is what is H? We have to find out, that is QS double dot divided by TS minus TM. It is minus 2C2 K divided by R0 divided by minus C2 by 2. Okay, so if you cancel this, you will get 4K by R0. So what is Nu? That is HD by K. So H is 4K by R0. What is D? 2 times R0 by K. R0, R0 cancels. It becomes 8. So I hope this was clear.
Yes, sir.
Yeah. Okay.
But sir, I have one doubt that why we are using RO instead of RI when there is an internal flow.
Because it's a thin wall tube. Means it's like what it is. So this is I meant by R0. Means it's like it's not the outer radius of the pipe, it's the surface of the pipe. Okay. You can call it of R0 or Ri any value. Here we are not concerned about the thickness of the tube or nothing. Here our concern is the T ranges from R is equal to 0, which is at the middle of the pipe, to the surface of the pipe, which is I am denoting it as R0. So you can take it as big R. That is not a problem. Okay. I hope it is clear.
Yes, sir.
It's not the outer radius of the pipe, it's the inner radius. So here, okay, if you have any confusion, you can use big R also. Okay, let's move on to the next question. We have a steam which is condensing on the outer surface of a thin walled circular tube of diameter 50 mm and length 6 meter, maintains a uniform outer surface temperature of 100 degrees Celsius. So the water flows through the tube at a rate of 0.65, 0.25, and the inlet and outlet temperature is given. So what is the average convection coefficient? So this is the same question we have already solved, I think, in the second question. It's just uh, there we have to find out N. Here we have to find out what is the average convection coefficient. So I will give some 3 minutes. So please solve it. Please, uh, I need an answer for this because it's just we already solved the same kind of question. So I hope you can solve it. Excuse me, I will come back in 2 minutes. Okay. Have you got the answer?
So I'm just calculating.
Okay. Did you got the answer?
Yeah, 755 watt per meter square Kelvin.
Yes, right. So I will
Seven
just
five.
solve it. Yeah, you're right.
Okay.
755, right?
Yes.
Yeah. So we have the energy balance, which is H average heat transfer coefficient, is LMTD, which is should be equal to MCP delta T, or we can say TMO minus TMI. So because it's a steam condensing, it's a constant surface temperature condition. So we have to find out the LMTD, which is equal to delta T minus delta Ti by ln delta T by delta Ti. Now delta T is Ts minus TMO. What is how much it is? 100 minus, sorry, surface temperature is 100 minus 57. It is 43, right?
Yes, sir.
Delta Ti is Tsi minus Tmi, which is 50.
85.
So 100 minus 50 is 85.
Yes.
So what is the LMTD? That is 85. Sorry, 43 minus 85 divided by 100. 43 by 85. What is the LMTD?
61.6.
Yeah, 61.6 degrees Celsius. So now we are just substituting the values f dot Cp Tmo minus Tmi by As, which is pi TL times LMTD. So what is f dot, which is 0.25 Cp 4178 you can take. Then 57 minus 50. Area is pi into 0.05 into 6 into 61.6. So this will come out to be 755 watt per meter square. Okay, then we will move on to the next question. So that was a very simple question and a direct question. So here in this question, we have a hot air flows with a mass flow rate of 0.05 kilocalorie per second through an uninsulated uh, steel metal duct of 0.05 meter, which is a okay. The hot air enters at 103, and after a distance of 5 meter of the length of the along the length of the pipe, it cools down to 85 degrees Celsius. The ambient heat transfer coefficient between the duct outer surface and the ambient air is 0 degree. At 0 degrees Celsius, the ambient air is at 0 degrees Celsius is 6 watt per meter square Kelvin. Calculate the heat loss from the duct over the length L. This is a it's direct equation, so it's single step answer.
Sir, here hydraulic dye is to be used.
Yeah, means for Q, I think you can directly get right? MCP dt. Here is a hydraulic diameter 0.15. What is the heat loss over the length L?
The specific heat is not given.
So CP of air, okay. You can take CP of air as 101 joule per kilogram. You can take this as CP of air. It's just Q is equal to m dot CP TMO minus TMI. So m dot is given 0.05, CP is given, and it is 85 minus 103. What is the answer?
Sir, 859.4 watt.
85,
859.4 watt.
859.
0.4 watt.
Can you please cross check? I'm getting a different answer. Here, please. I'm getting 910. Can you please cross check your answer?
It's 909.9.
Ah, okay.
Okay.
It's almost close to 910. So it's negative because the air is losing heat. Okay. So that is the first part. So in the second part, we have to determine the heat flux and the duct surface temperature at x is equal to L. So two quantities we have to find out here. We have to find out the heat flux and the duct surface temperature at x is equal to L.
For heat flux, we have to use the area and for area we have to use the hydraulic area, hydraulic dia.
Yeah, hydraulic diameter. Now for heat flux, here we cannot actually uh, define the what to say. Here it's not the constant surface heat flux or uh, versus surface temperature boundary condition because the heat is losing along the length, right?
Yes, sir.
Yeah. So we have to find out the local thing, local heat flux. So you cannot divide this 910 by the surface area. You will get an average heat flux, but it's not at the x is equal to L. I hope you understood.
But sir, in that question number 7, you please show that. Yeah. Calculate the heat loss from the duct over the length L we are calculated. So that is the
Uh,
total length.
yeah, on the total length.
Yeah.
Yeah,
So this is the total heat loss from length L.
yeah. This is the total heat loss from x is equal to 0 to x is equal to L.
Yes, sir.
Yeah.
So now why we are moving to the local?
I, I am asking heat flux at x is equal to L at a specific point. Heat flux. It's not the heat.
Okay, okay.
I'm asking heat flux.
So can you show the statement?
Are you getting the answer?
No, sir.
Okay. So if we draw the resistance network at x is equal to L, okay. So we have the convection resistance, okay, and it is told that the heat is getting transferred from the outer surface of the wall to the ambient. We have to consider that resistance also, which is 1 by HO, which is uh, which is same all over the line. Okay. So what we need to find out is
So
HO.
conductive resistance we are neglecting.
Yeah, we are neglecting conducting system.
Okay.
Okay. If if the diameters or the inner diameter and outer diameter and the thermal conductivity is given, we have to consider that also. Okay. Here we are assuming that it is a very thin wall, thin duct, so that there is no conduction resistance. So this is the heat flux QSL. This is the one we have to find out also. So the heat flux at L is equal to TML minus T infinity divided by 1 by HXL plus 1 by HO. Okay. So HO we already know. TML is also we know that is how much 85 degrees Celsius, and T infinity is also no zero. We know it's 0 degrees Celsius. So what we have to find out is the HX or the heat transfer coefficient at L, the inside heat transfer coefficient. So for that we have to find out the Reynolds number to determine which regime it is. So this is 4 into what is 0.05 into pi into 0.15 into mu. Okay, oh, its properties are not given. So mu it is 217 into 10 raised to minus 7. So if you calculate this, you'll get some 20,050 as a Reynolds number. So the flow is turbulent. Can you please check whether we can assume the fully developed regime? Calculate L by D is 5 divided by 0.15. What is L by D? Can you please calculate?
33.3.
Yeah, it is 33.3, which is greater than 10. So we can assume the fully developed condition. Okay. So now we will go to the Ditterboiter equation. That is NUD is equal to 0.023, Knowles number 455, Prandtl number is 2.3. So please find out what is this. Here, yeah, here why I use 0.3 here.
Because it is cooling.
Yeah. So the Prandtl number you can take as 0.698. Can you please find out what is the Russell number? I think you will get the value of something 56.4. Are you getting this?
I'm getting 57.1.
Okay, fine. So now you can find out what is hx, which is equal to 56.4 into uh, 0.0306. That is the k value divided by 0.15. So you will get around 11.5 watt per meter square Kelvin. So now you can find out what is the heat flux. That is 85 minus 0 divided by 1 by 11.5 plus 1 by how much is HO? It's 60. Sorry, 6. Okay. So you'll get the heat flux as at exit as 335 watt per meter square as the heat flux. So now you can easily find out what is duct surface temperature, because this is a resistance network. We already find out what is the heat flow. So just use the equation, that is the same resistance network concept. So the Q, this quantity we already find out. So TSL is equal to, it will be around 55.9 degrees Celsius. I hope this was clear.
Sir, here we are using HD, like we have used for some number HD by K. So this dia will be hydraulic dia.
Yeah, hydraulic tire.
Okay.
Okay, let's move on to the next question. An uninsulated air conditioning duct of rectangular cross section, given the area carrying air at 20 degrees Celsius with a velocity of 10 meter per second, is exposed to an ambient of 30 degrees Celsius. Neglect the effect of duct construction material. Okay. The air is in the range of, and the data is given. So the laminar flow Nusselt number is given 3.4 for constant wall temperature conditions, and for turbulent flow, our determinant equation is given. So we have to find out what is the Nusselt number of the flow. Sorry, Reynolds number of the flow. I will wait for 2 minutes because this is very simple part. You got the answer? Reynolds number.
No, sir.
It is
Most of
simple.
it. 1. Certainly not. 2. Certainly not.
So the Reynolds number is rho v, the hydraulic diameter divided by mu. What is the hydraulic diameter? 4a by the wetted perimeter, which is 4. Here it is a rectangular duct, so it is the cross-sectional area is a into b. Perimeter is 2 times a plus b, which is 2ab by a plus b, which is equal to 2 into 1 into zero point 0.5 all divided by 1 plus zero point 0.5, which will come out to be around 0.666 meters. So, okay. So the Reynolds number now it's simple, that is rho v dx by mu, that is 1.2 into 10 into 0.66 divided by, that is mu, 18. 18 into 10 raised to minus 6. So it will come out to be around 4.44 into 10 raised to 5. What was the doubt in this? This was a
Actually,
simple question.
my doubt is like, sir, please show the statement that the laminar flow Nusselt number is already given,
Okay,
and the for turbulent relation is given.
okay.
So then this relation and turbulence that will be so it will not be having any use if we are directly calculating Reynolds number.
No, in question there will be there can be some extra information also. It is not necessary that whatever image, whatever we need to, these are extra information. Okay. So in some question, this may be given to misguide you also. So let it be there, because in the question it is not at all telling that it is a laminar flow or a turbulent flow. So they are just giving, if it is a laminar flow, then Nusselt number is 3.4, and if it is a turbulent flow, it is you have to use this Nusselt number value. So in any part of question, is it is written whether it is laminar or turbulent.
But sir, constant temperature condition they are writing like laminar flow Nusselt number
What I
3
don't get.
for constant wall temperature condition it is written.
Okay.
So is it that relevant that there is no constant temperature condition?
No, the question it is asking Reynolds number, right? So if you are asked to find out something, I don't know why you are going guessing something.
Then it is simple, sir. Then it is very
Yeah,
simple.
what was your problem?
My
Why
problem,
you
I got confused because of these relations. That which relation I should use, but then Reynolds number. Yeah, that was the main confusion. That
yeah, that was given as an additional information only, because
okay.
for finding Reynolds number, everything rho v d is the one we have to find out. Mu, everything is given. There
Yeah,
is,
everything is given. Yes, so that much hydraulic die I calculated. Then I thought that laminar can for laminar 3.4 for turbulent. Then what is the use of this? If I'm using the formula dv rho by mu.
okay. So
Okay. Yeah.
okay, fine. So okay, that was for this part of question. Maybe uh, there will be, please expect, there will be some in some cases there will be some extra information given in the question. It is not necessary that you should use that information to solve the question. Okay, there may be
Yeah,
say for
that is
example,
okay. But see,
yeah,
that the previous question that at constant temperature, it is written. But
Okay.
that condition is not constant temperature. I think that statement is contradictory. No? Is it like laminar flow lesson number 3.4 for constant mode?
That is what I am telling. So it's not relevant to the question, but it is given as some extra value. The statement is true, right? For laminar flow Nusselt number, it is 3.4 for constant temperature conditions.
Yeah,
It is given as some
true.
extra additional information.
Okay, sir.
Yeah. So in this question, what we have to do is we have to find out the heat transfer per unit length of the duct. So we already find out what is the Reynolds number, which is anyway in the turbulent regime. Okay. So the Nusselt number is also given, but that is here I should use 0.3 or 0.4.
Point 4.
It is a cooling case, right?
No. 0.3 is the
Yeah, it should be 0.3. So the Reynolds number is 5.
I think it should not be 0.33, it should be 0.3 exactly.
Yeah, okay. It is here. It is given. We are asked to take this one. That's why I've taken. You can take 0.3 also.
Okay, okay then.
There is
Okay.
no much difference. It will come.
Okay.
So the Prandtl number is point. How much? What is Prandtl number? 0.73. So the Russell number will come out to be okay. So what is value of H? Is Nu K by L is thermal conductivity 0.025 length is 0.66. Okay, this is not L, this is T. Which will come out to be around 25.6 watt per meters per Kelvin. So you are asked to find out the heat transfer per unit length of the duct. Okay. So what is the cross-sectional area to A plus B, that is perimeter times the length of the duct. Okay. So Q is equal to HA T1 minus T2. The average, you already found out the average heat transfer coefficient, which is 25.64. That is H2A plus B times L. Sorry, this is so we are asked to find out Q by N, which is equal to 2H times 2A plus B Tm I minus T0 is equal to 2A plus B is 1 plus 0.5 into 303 minus 293. Or you can say 30 minus 20 also. I just converted. Both will be same as it is a temperature difference. 30, 20. So you will get the answer as around 769 watts. Okay. I hope this question was clear. So if the length of the duct was given, we will get the total heat transfer. Here, as the length is not given, you are finding out the heat transfer per unit length. Okay. So today we are so it comes to the end of our session for today. So I hope this session was helpful for you and you have learned some new kind of questions. Okay. Have you tried this kind of questions earlier? Means I am trying to pick maximum variety type of questions so that you will get an of overview of every type of question can be asked. Okay.
Yes, yes, sir.
Yeah. So then we will stop. We'll wind up the session here. So have a nice week ahead and thanks for joining. And see you next Monday, 6 o'clock
Okay, sir. Thank
in
you.
the evening.
Thank you.
Thank you. Thank you.
Thank you, sir.